Hi, in this talk, I'm going to talk to you about classification of distributed binary labeling problems. This is joint work with Alkida, Sebastian, Juho, Yannick, Denis, and Yuka. So in this talk, my goal is to convince you of the following sentence, that the distributed complexity of homogeneous binary labeling problems on trees is decidable. We are going to break this sentence down into its components and understand them one after the other, starting with distributed complexity. And what do I mean by that? Well, in this talk, we are going to focus on the local model of computation, in which we have a network of n nodes. Each node has a unique identifier. Communication takes place in synchronous rounds. The initial knowledge of each node is only its immediate neighbors. And we have unbounded local computation inside of each node. And our complexity measure is going to be the amount of rounds. Next, we are going to talk about binary labeling problems, starting with an intuition to what binary labeling problems are. Well, in a binary labeling problem, our goal is to label the edges of a given graph, either red or blue, such that some radius 1 output constraints are satisfied. For example, in this tree, this is a labeling of the edges in red and blue. To be a bit more formal, I'll define binary labeling problems in the next slide. But before that, some examples of binary labeling problems include two coloring, perfect matching, simplest orientation. Now, you might think it odd because two coloring, for example, is a vertex labeling problem. So how can I represent it using labeling edges with colors? I'll elaborate on that later. So now, to be a little bit more formal, we are given as an input a two-color tree with black and white vertices, where the tree is properly colored. While this seems to weaken our results that I'll talk about next, this is actually not the case. And in fact, the fact that we are given a two coloring allows our model of problems to be much more expressive. So to be formal, a binary labeling problem is a tuple with D being the white degree, delta being the black degree, and W and B are the white and black constraints respectively. And what do I mean by that? Well, we are going to have that Wi is 1 if and only if white nodes are allowed to have I incident edges colored red in the final solution. And similarly for V. So now let us take an example for a binary labeling problem. Specifically, let us look at the following problem. And well, we can see from its definition that white nodes are required to have at least one red edge adjacent to them in the final solution, and black nodes need to have exactly one red edge adjacent to them in the final solution. So for example, this is a valid solution, but this, however, is not, because as you can see, the white vertex on which the arrow points has all of its incident edges colored blue. So we can you might see that this problem is actually the simplest orientation problem on graphs of degree 4. And why do I claim that when we have black vertices of degree 2? And here is where I show you why we can assume without loss of generality that we are given a two-colored graph, at least in the case of black degree 2. This is true in higher black degrees as well, but I'll explain it only for black degree 2. Well, assume we didn't have the black nodes and we wanted to solve Sinclair's orientation on this graph. Well, what the white nodes could do, they could simulate the existence of these black nodes and then solve the binary labeling problem with a constant overhead in the round complexity. And so after they solved the binary labeling problem described here, they could just direct red edges to blue edges, thus giving them a valid solution to Sinclair's orientation, because every white node has at least one outgoing red edge. Thus, having black nodes of degree 2 doesn't really restrict the descriptiveness of our model, but actually it allows us to simulate port labelings, for example. Thus, the two coloring is given without loss of generality. Yes, and this is the final solution. Now, there's one little thing I need to talk about, and it is that we are focusing on homogeneous binary labeling problems. And by that, I mean that we don't really care about the degree of, about the output of low degree vertices. So for example, if we have leaves, then we don't pose any constraints on their radius 1 output neighborhood, and any labeling of their incident edges is going to be valid. So now let us get to the main theorem and what I mean by decidable. So our main theorem is as follows: that the deterministic complexity in the local model of any homogeneous binary labeling problem is one of the following. Either it's O of 1, and not only that, it turns out that all the binary labeling problems that have complexity O of 1 are actually exactly the problems which are solvable in 0 rounds of communication. From there, we immediately jump to theta of log n with nothing in between. So in particular, theta of log star n disappears, which is kind of surprising because many known and important symmetry breaking problems, such as maximal matching and maximal independent set, are known to admit theta of log star n around algorithms on bounded degree graphs. That means that these problems cannot be represented using only two labels. From theta of log n, we immediately jump to theta of n. And here you would have all the problems that you would guess that will have global complexity. For example, two coloring and consistently orienting a tree from some given root. And lastly, we have the unsolvable problems, which are basically problems which they're right in their definition. There is a contradiction, and it's clear that a problem cannot be solved. That is, there is no feasible solution to the problem. Furthermore, given the description of a binary labeling problem, one can very quickly find its complexity and the optimal algorithm solving it. This is depicted in the following table. So if we have the following legend, where this dot means it can either be or 0 or 1, we have that unsolvable problems are problems that have the following type, and as you can see, it is very easy to check whether a given binary binary labeling problem matches this pattern or not. And the same holds with O of 1 problems, and the same holds with theta of n problems. And well, all other problems actually have complexity of theta of log n. So now we are going to dive a little bit deeper into this theta of log n complexity regime. And well, here we have 4 types of problems. One large family that's called 1-2 resilient or 2-1 resilient problems. And then 3 special problems, which did not fall into this characterization of resilience, but I will not elaborate on them much. I'll just name them for completeness sake. These are the bipartite matching problem, the hypergraph matching problem, and the edge grabbing problem. So in order to explain to you what I mean by 1-2 resilient or 2-1 resilient problems, let us go back to a moment to our example and this cute tree that we had. But now instead of focusing on the syncless orientation problem, we're going to change the problem a little bit by moving the 0 one coordinate to the right in the white constraint string. So now white nodes need to have not exactly one red edge, while black nodes still need to have one red edge. So for example, this solution is bad because we have a white node with exactly one incident red edge. But we can easily fix that. But now you could ask, well, how could I have solved this problem in the local model of computation? And for this, we use the well-known tool. Oh, yes. We call this problem the forbidden degree 1 problem, because basically white nodes are not allowed to have output red degree 1. And well, to solve this problem in the local model of computation, one can follow the well-known iterative procedure of layer decomposition, in which we create layers of vertices by iteratively removing black vertices of degree at most 1 and white vertices of degree at most 2. So for example, in this graph, first of all, the white leaves are going to be removed, then the black leaves, then the remaining white nodes, then the remaining black nodes, until we are left with one vertex. Now one can one can go in the reversed order of the layers in order to label all of the edges to create a feasible solution. So we start with the last layer, which in this case is only one vertex. And so this white vertex labels his incident edges in a feasible manner. Then you can see that while all black vertices already have one edge, which was already labeled, they do have the option to complete their labeling in a valid manner. And the same holds for these white vertices here. Although already one edge in their a radius 1 neighborhood was already labeled, they have the option to complete their labeling into a feasible solution. And we continue as such. One can very easily show that this layer decomposition will have only theta of log n layers. I'm sorry, O of log n layers. And so this entire algorithm will take O of log n rounds. And what I mentioned here is the ability of white or black nodes to complete a partial labeling to a full feasible labeling of the radius 1 output neighborhood, we call this property resilience. And it is actually, we prove this, very easy to check if you just look at the string that defines the binary labeling problem. So given a binary labeling problem, where we are going to say that it's TS resilient if the wide constraint string does not contain the substring 0 d minus t plus 1 times as a contiguous substring, and similarly B that doesn't contain the substring 0 delta minus s plus 1 times as a contiguous substring. So for example, this string, this binary labeling problem is 2-1 resilient. The problem we see at the left bottom corner at the top, because, well, you see that the wide nodes do not have 3 zeros in a row, which makes it 2-1 resilient. But the problem on the bottom left corner is not 2-1 resilient. And similarly for B, we have problems that are 1-2 resilient, but in problems that are not 1-2 resilient. And basically the theorem that we show is that if a binary labeling problem pi is either 1-2 resilient or 2-1 resilient, and is not, of course, solvable in 0 rounds, then it has complexity O of log n. And also we show that for these 3 special problems that I've mentioned before. Now I'm going to briefly, very briefly, talk about how we show the lower bounds for all the problems in the class of theta of log n. And so our main tool here is the round elimination technique, on which unfortunately I do not have time to elaborate. However, our starting point here is the problems that I've mentioned, the forbidden degree problems, whose general form is as follows. Basically, wide nodes are not allowed to have one specific degree of degree output. And so by taking the forbidden degree problems together with the Sinclair's orientation problem, we were able to relax both of these problems into a problem we call forbidden degree, or Sinclair's orientation problem, which is an LCL with 4 labels. And for this problem, we were actually able to show an omega of log n lower bound using the round elimination technique by proving that this problem is in fact a fixed point. And now I'm going to talk about a little bit about randomized classification, which we also began to explore in our work, although there are still open cases remaining. Well, what happens in the randomized regime is that, well, theta of log n splits, the deterministic theta of log n splits into problems that have randomized complexity theta of log n, and problems that remain with complexity theta of log n, even in the randomized regime. Example of a problem which has theta of log n complexity is Sinclair's orientation, while, for example, perfect matching still has theta of log n complexity. And as I said, the classification is not complete, and there are open cases remain. I'm going to briefly mention some of the techniques that we employed in order to show lower bounds for the randomized complexity of binary labeling problems. There is a known lemma, which I'm stating here informally, is that for every d, which is at least 3, there are high girth graphs, namely omega of log n girth graphs, which are d-regular and have no large cuts. This allows us to prove that the following family of problems, for example, has randomized complexity omega of log n. And intuitively, this is true because every solution to this problem must induce in the graph a very large cut. But there are graphs in which no such large cuts exist. And they do, however, look like trees locally. So in order for each node to find out that the graph is not a tree, one needs to look very, very, very far, namely theta of log n distance. Also, we define the notion of an escape for a binary labeling problem, which is very, very, very simple. We say that a problem pi has an escape if either W or B contains the substring 1 as a contiguous substring. So for example, this problem has no escape, while this problem has an escape. And our theorem is that if pi has no escape, pi has randomized complexity, theta of log n. So to sum up, I'll repeat our main theorem, and that is that homogeneous binary labeling problems in the local model are either trivial, that is, of 1 rounds, and even actually 0 rounds. They either have complexity of theta of log n, which we call local, or they are global. That is, they have complexity theta of log n, or they are unsolvable. This is actually the first step towards like automatizing algorithm design for distributed computing, because just giving the description of the problem, you can not only find out its complexity, but actually the optimal algorithm solving it. And so as open problems, we leave the randomized classification, which, as I said, still has some open cases remaining. And what happens, for example, with problems with more than 2 labels? We know that things already get a bit more complicated, because we know that the complexity class of theta of log star n appears already at 3 labels, for example, for maximal matching and maximal independent set.